Hello world, it's Craig. Continuing with the Intellec 8 series, we finished discussing this 4K RAM and the 4K PROM boards in the last two videos. And this is my reproduction of the imm8-82 CPU board. It's based on the 8008 processor. And more specifically, I think they were all for the 8008-1, which was the higher performance selected version of the 8008. And here selected basically means Intel tested the processor, to its limit, and if it was above a certain performance threshold, it was selected to be a -1, and if it didn't, then it was just a straight 8008. So with the RAM and the PROM boards, I covered one board in each video, and that was relatively easy because, if you look at these, for the most part, it's a pretty simple board. There's, just a lot of chips in parallel. There wasn't a whole lot of logic going on to this. And I expected that most viewers had a good grasp of the chips that were involved, and I didn't need to explain the basics like decoders and multiplexers and the like. But when we start talking about the 8008, I think that I'm assuming there's larger gaps in knowledge when it comes to the 8008. So we're going to do this a little bit differently and break it down into bite-sized pieces. This video is going to be an overview of the board and how it generally works in an Intellec 8 system. And if you watch the PROM and RAM videos, you have an idea as to what signals are expected of the CPU board in order to get those two to respond to the memory cycles properly. Let me move this out of the way so we can look at this board. If we look at the subsystems on this board, the first thing is the clock. And in the top center of the schematic is the clock generator, and this has a 5.587 megahertz crystal driving this oscillator circuit. And that oscillator then goes through a little bit of logic to create the two clock signals required by the 8008. And these are Phi 1 and Phi 2. As far as things go, it's a pretty simple clock. It's a tad more complicated than the 4004 and a tad less complicated than the 8080. This board creates both clocks and their inverted values for use around the board. So here on the board we have the crystal up here in the top right hand corner, and then down along in row B we have the inverter in B9, the counter in B7, and the latch in B6. So we will talk about the clock for the 8008 in its own video. Next up, let's look at the data path. Go back to the schematic. Now over in the top left we have the data buses on our card edge connector. And these squared numbered boxes are the pin numbers where the card connects to the backplane. In the Intellec system, there are 3 individual 8-bit data buses, and all of them are unidirectional. They're bringing data from the backplane devices into the CPU board. There's the memory data bus, and remember, for both the PROM and the RAM board, they had the data memory output bus that they put the data on during a memory read cycle. And that's a one-way bus that starts at any of the memory cards and it ends here on the CPU board. Now there's 8 memory card slots on the backplane, and those memory card slots are just in parallel for that bus. And throughout the data path, they're handled as a byte, but on this diagram they're split into the low nibble and the high nibble just for convenience because these are 8-bit or 4-bit chips. That read from memory data bus nibbles are this very top one and this fourth one down. So this is the low nibble, this is the high nibble. There's a similar bus coming on the backplane from the I/O cards, and that's called the input port data. That input port low nibble is the second from the top, and the high nibble is the second from the bottom. And then finally, there's a third bus for the input, and that's the interrupt instruction port data, which is how an instruction is jammed onto the bus during an interrupt cycle. Low nibble is the third one down from the top, and the high nibble is at the very bottom. These all have 1K pull-up bus terminators, and they enter into a pair of 8263s, which are 4-bit, 3-input multiplexers. One for the low nibble here in A7, and one for the high nibble over here in A9. On the board, there are these big boys down here at the bottom right. And it's a funny thing about these Signetics 8263 is that many of the parts only had the number on the bottom. I've ordered these from a number of sources and they've all only got the number on the bottom. If you plan on building this board, you want you'll want to call up Anchor Electronics and order some of these. I think they have them listed right now for $1.50, which is a fantastic bargain. So, and if you get them from Anchor, the tops were originally blank, and so Anchor had the part number printed on the top of these chips. But anyway, if you are getting some 8263s, you want to call up Anchor Electronics for them. In any particular read cycle, we only need data from one of those three sources. So the glue logic on this board selects one of these three backplane buses using the multiplexer. And here between the multiplexers are the two selection lines, and they select from the A, B, or C input, and they drive these onto the Q outputs here on the right side of that chip. Between the multiplexers, this is a third input that when it's asserted, it complements the outputs, but it's tied low, so it makes the outputs the same logic as the inputs. We're not using that in this board. From the multiplexers, the data byte is presented to these 8093 tri-state buffers. And these buffers are asserted by a signal coming from the bottom logic called the D bin, or the data bus in. And that's a name that we're all probably familiar with from later processors like the 8080 or the 8085. But here it's a board generated signal. So D bin is a board generated signal, active low. Anyway, whichever bus data was selected by the multiplexers, it's held off by these 8093s until the CPU is in an appropriate data read cycle. And then when D bin is asserted, the drivers are enabled, and the data bus is presented to the 8 data lines on the 8008 that are now in input mode. D bin also turns on these pull-up resistors to minimize data bus loading and increase the bus response. These weren't required with the straight 8008, but the -1 needs them in order to operate above 500 kilohertz. And if you are lucky enough to have an early SIM 8-1, these pull-up resistor diode pairs aren't even on that one. Here's the 8008 processor down here on the schematic, and on the circuit board, it's right here in the middle. This is the 8008, and over here to the left on the board, these are those pull-up resistors and the series diodes to pull up that data bus. Now the 8008 only has 8 data lines. They're bidirectional, and they're doing quadruple duty. The first function is to input data to the processor through the path we just talked about. And while that data is the only input, there's several output modes for this. All of the time wasted multiplexing is, of course, because Intel refused to go beyond an 18-pin package for the 8008. And that's why, others had already gone up to the 40-pin package. And, even Intel was using 24-pin packages for EEPROMs. The 1702A was in a 24-pin package, but Intel refused to go up above 18 pins. In fact, if you listen to some of the things, even getting to an 18 pin was a battle. They wanted to make this a 16 pin. So, the 4040 got a 24 pin dip. So why was the 8008 forced, it was force fit into this 18 pins, and that really, really limited this. It's like somebody at Intel wanted this 8008 to be a failure by hobbling it in an 18 pin package. And we'll see that theme come up time and time again with the 8008 and how it was designed from the onset to underperform. Okay, so back at the topic at hand, we had gotten to the data input to the 8008. So now let's look at the data output, which is everything here on the right side of the schematic. So on this whole schematic, everything on the left is coming in, on the right is going out. During an output cycle, that data is put onto this output port where it's buffered by this exclusive OR. And while we're here, using an exclusive OR here seems like a bit of an odd choice. And I would challenge anyone to tell us why that device was chosen. There's a very good reason that I think that is a good reason, and we'll get into that into another video. But in the meantime, it should really be gnawing at you why, of all things, an exclusive OR was chosen as this buffer. It seems like maybe the logical thing would have been just to go right into these 8093 buffers. But I'll save that for a future video. But you can see these exclusive ORs have one input that's just tied to ground, so they're not inverting the signal, they're just buffering it into the data bus output drivers here on the right. Like the data bus in signal, the D bin, there's a data bus output signal that's asserted to enable those drivers during the appropriate time in an output cycle. Once the output data gets through those 8093 buffers, there's 3 sets of output latches. So this fans out to these 3 output latches, as well as just going directly onto the backplane here. The top 2 latches are the low and high nibble of the low address byte. Early in a machine instruction, the 8008 puts the low address byte onto its data bus, and that's gated into these 8T10s, and that sometime later a strobe latches that data into those latches. The outputs of these they're almost always enabled, so that low address byte is almost always available to the signals on the backplane. So everybody else on the backplane gets that low address byte essentially all the time. After sending out the low address byte, the 8008 will send out the high address byte, and that's captured by these next 2 8T10 quad latches. Since the 8008 is only a 14-bit machine, only the bottom 6 bits are address. The top 2 bits are not address, and rather they're status bits, but we need them anyway, so they're latched along with the 6 address bits just to get it done. And again, the output of these is almost always enabled, and the high address bits are almost always available on the bus to all the cards on the bus. And I keep saying almost because this board allows for another device to assert the hold signal to request control of the backplane bus. And during the hold, this CPU card needs to relinquish the bus and stop driving all of the output lines. So the output to these latches is actually controlled by the hold acknowledge signal. You can go back and look at the video on the little STD card that I made, and there's a little bit more about putting the bus into a hold so that somebody else can do DMA and that kind of thing. So even back in this, this is 73, that they had this in mind for the ability to do DMA. Since the processor doesn't generate the top 2 address bits, there's solder bridges here to tie the top 2 address bits low when you're using the 8008 card, and if you're using the 8080 card in this intellec 8, then those are controlled. According to a note in the bottom of the schematics on the original Intel board, there are traces that need to be cut if you want to configure it any differently. Under the high address bit latch, the next space down, we can see that the data lines are directly driven onto the backplane as the data bus out. And that's the data bus that goes to everything in the backplane, maybe except for the PROM boards, but it's used for RAM writes, port output, and the front panel. But notice it isn't latched, so it's as transient as the 8008 wants it to be. These 8T10s are the first 4 along the bottom row right before the signals are driven onto the bus fingers. And if I remember correctly, Anchor Electronics has the 8T10 for $1.75. So again, a fantastic price. You'll pay 5 or 10 times that much if you just go to eBay and get them. So go to Anchor Electronics, you get a nice stockpile of these 8T10s, while you're shopping for those multiplexers. Finally, there's 2 more 4-bit latches, and these are Intel's favorite latches, the 3404. We'll get to this data in another video when we talk about machine states in the 8008, but for now it's enough to understand that they latch some processor status flags and state data onto the bus for use by the front panel. All of this logic in the bottom half of the schematic is the glue that's required to make sure everything happens in the proper sequence and at the proper time. This is what controls the selection of which input data bus was selected by these 2 multiplexers. And then when that data is then presented to the CPU, when the low and high address bytes are latched onto the backplane, when the external RAM write strobes are created, this is how the board handles interrupts and halts and so forth. So all of that is done by all of this glue logic here on the bottom half of the schematic, and essentially this entire board is just glue logic except for what's directly related to the 8008. And it's all this stuff at the bottom that gave the 8008 such a bad name. Many engineers that look at it and say it's just not worth the effort. And even more frustrating, everyone that was designing their own system based on the 8008, they had to go through and create the exact same signals, and all of this logic could have been implemented by a single 8008 support chip if Intel had been so inclined. So instead of making everybody do all of this support logic, they could have just put out one chip that handled all of this. And eventually all of this logic got built into the 8080, and there was still a bunch of glue that had to be supported on the 8080 to get the timing correct. But then for the 8085, all of that support logic got built into the 8085. But by golly, they really could have made this 8008 a better success, or a bigger success, if they had incorporated all of this glue logic into one little 24-pin DIP that you just plug in, get rid of all that glue logic for you, since everybody had to do the exact same stuff. You know, here's the imm8 CPU schematic, and it's just a mass of logic gates and latches that could have been replaced with a single support chip. Here's the Mark 8, same thing, just a massive logic gates and logic that could have been done with one chip. Anyway, on the imm8-82 board, you know, even if it's for nobody else but, you know, my future self trying to diagnose a problem, I'll go over this support logic in other videos, and we'll probably be breaking those down into little bite-sized subsets. But in this video, we're just going to break the glue logic down into, you know, general subsections. We can see on the left here, there's 5 backplane signals feeding into this glue. They're all active low, but I'm not going to mention that each time. So all of these are active low. From top to bottom, there's a wait request that requests the processor to insert a wait state, so a port or some memory or whatever can catch up with the processor. There's a halt interrupt request, and this is a request to do an interrupt if the processor is already stopped. So if it's already in a halted mode, then it'll generate an interrupt request. The next one down is the actual normal interrupt request, and that's just as normal use. There's the hold request, and that's request a hold operation, and that's when some other processor is going to take over the bus, and so this card then has to relinquish all of the bus control, and it has to, you know, tri-state, take all the signals off the bus so that somebody else can use the bus. Then there's this interrupt jam enable, and this enables an input jam operation. You know, presumably it's going to come from the front panel, so you can have an input to a port, but rather than have it actually get it from the port, you can force that in from the front panel, and that's what this interrupt jam enable does. You know, timing of external signal into the 8008, it's critical, and it must be accomplished by this board logic, since input gating was not designed into the 8008 at all. If you want to give it an interrupt, that interrupt has to come in at a certain time, or that 8008 is going to ignore it. And towards the left here on the schematic, we've got 7 latches that latch the various requests until the processor is ready to receive that signal. And you can see they've got names, which, you know, fortunately for anybody trying to understand what's going on, you know, fortunately these are named on the schematic, and the names are like, you know, interrupt request latch and interrupt cycle latch. So here the interrupt request latch captures the interrupt request signal, you know, that came in off the board, and holds it until the processor is ready to be interrupted. And then when the processor is ready to be interrupted, it gives it to the processor. And then when the processor goes into the interrupt cycle, that latch is cleared and the interrupt cycle latch is held, meaning that we're in an interrupt cycle. And I think we can generalize by saying that all of these latches do that sort of essentially stretching signals or delaying signals until the processor is ready to listen. There's a little bit of logic here to help set up and clear the latches that are to the left. There's 2 decoders on this board that determine what the 8008 is doing. Here, D2 is a state decoder. It's a 3205, which is the 3 to 8 decoder. It's a predecessor of the 74-138, and you can get by using a 74LS-138 instead of that 3205, but it has to be a low-power Schottky, or at least a low power. It has to be at least a 74L138. Over here is D10, which is another obviously underutilized because it only uses 4 outputs, and it's the cycle decoder. So the first was a state decoder, and this is the cycle decoder. The first one, the state decoder, D2, tells us which of the 8 internal states that processor's in. It takes status lines from the 8008, and it uses those to determine if it's reading data off the bus, if it's writing the low address byte, writing the high address byte, if it's in an interrupt cycle, if it's waiting, if it's stopped, and so forth. The other one is the cycle decoder, and that was D10, and it paints with more broad strokes, and it tells us what type of machine cycle the processor is executing. Is it an opcode fetch, for example? Is it a memory read? Is it a memory write? Or is it port I/O cycle? So those are the only 4 types of machine cycles: fetch an instruction, read or write memory, or port I/O. And there's an appreciable amount of glue logic here to get all of that timing correct, and we can see the signals that this board then presents to the backplane. And some of them are very familiar from the other processors or from the other cards that we looked at. We have acknowledges for the halt. So we've got a halt acknowledge, we have an interrupt acknowledge, hold acknowledge, and a wait acknowledge. There's a normal read-write line like we would expect or we need. And then, much like the Z80 would later adopt, we have individual lines for I/O output, I/O input, memory read cycle, and memory write cycle. So this is all broken down and it's spelled out for us so the individual cards don't have to decode any of that. It's just individual signal lines to tell them what to do. Now finally, we have a number of signals that we usually don't get to see off board. And that's because this was designed to have a front panel. And these are things like the data bus in and the data bus out signal. So that deep in and that deep out signal that we saw earlier. The two signals that they gated the data into and out of the processor. So it's nice to have those on the back plane if we want to pick them up with our logic analyzer on the front panel. A fetch cycle telling us that the CPU is getting an opcode, and some status signals that just tell us what's going on, like T1, T2, T3, T3A, interrupt request latch, and sync A. And we'll get to all of those in a video on the 8008 machine states. It's also worth noting, looking down here in the bottom right of the schematic, what this board does not control. And some of these signals are just tied, or they're tied high or low, or they're just left floating. The stack cycle, interrupt disable, and reset, those three are just reserved for the 8080 board, not used at all on this board, not controlled. This board does nothing with the PROM or the RAM module enable. It just leaves the memory boards to duke it out among themselves. And it does not control a bus busy signal. That's just tied high. Now, for the most part, I have this board up and running. There's still some things that I haven't tried. I haven't done a hold request to confirm that it does indeed let loose of the backplane like it needs to so that somebody else can control the backplane. But it fetches instructions, it reads and writes memory okay, it allows me to jam an instruction onto the bus, and so forth. There could easily be some bugs lurking in this board that I haven't found yet. I did find, just like with my memory boards, I found that I missed a trace on this, and so there is one little patch wire that has to be added to the back on this version, and I'll take care of that in the next version of this board. So the next few videos will basically be learning about this 8008 in general, but mostly using this board and occasionally the Mod 8 boards as examples. But it's going to be learning the 8008 and using this board and how this board operates as a specific example. And the idea is to break the videos down, as I mentioned, into reasonable bite-sized pieces of information that they're useful to anybody that's interested in the 8008, whether it be for a Mark 8, the Mod 8, the Intellec 8, a Sim 8, or any other 8008 machine from that era. I think the next video will be about the clock, because even things like the clock isn't trivial for this, to get a good clock and to see how they did it on this. This is an all digital clock, not like a multi-vibrator clock that was used in the Mod 8 and the Mark 8. Then after the clock video, we'll talk about the processor states, and then we'll come back and talk about the data path, and then maybe 2 or 3 videos on this logic down here. We'll break the logic down into smaller bite-sized bits so it doesn't get too boring. And so let's see, that gives you 2, maybe 3 videos before we get to the answer as to why exclusive OR was the right choice for that data buffer coming out of the 8008. If you know the answer to that question, feel free to put it in the comments, but if you don't want to spoil it for everybody else, feel free to email me, and when we get to it, I'll mention anybody that pre-sent the answer so you can be sure to get your moment of fame for your efforts. Well, that's it for this video. Thanks for watching. I hope you find this interesting, and this is a fantastic piece of history, the Intellec 8. All right, talk with you later. Thanks for watching. Bye-bye.